moving on to 3 consecutive talks on gene therapy. And gene therapy, the approaches that are being taken are really a sort of a common approach, but we're going to hear about how they're being applied in different ways to different diseases. And we're delighted that Dominic Gessler, who's a physician scientist working with Dr. Gao at the University of Massachusetts Medical Center, is going to give the first of these talks on gene therapy. This is to do with CANAVAN disease, and he was funded in 2010 by NTSAD. So again, you can see how the research funding is really sort of stimulating research activity that's going on long beyond the funding period for each of these grants.
So my name is Dominic. I'm at the Gene Therapy Center at Dr. Gao's lab at UMass, and we're working on CANAVAN disease gene therapy. And I want to give you an overview over 2 important goals that we have achieved recently using gene therapy for CANAVAN disease. So for everyone who's not familiar with this disease, it's a rare disorder that's caused by mutation in aspartoacylase, which is primarily expressed in the oligodendrocytes in the brain. And when it's mutated, what happens is you have an accumulation of N-acetyl aspartate, or NAA. And here on this picture, you see Rachel and Jessica, which you might be familiar with. Jessica did an internship at Dr. Gao's lab to see what is CANAVAN research all about and how she can contribute and help to develop gene therapy for her sister Rachel, who has CANAVAN disease. People have been trying to divide CANAVAN disease into severe and mild forms, which is primarily determined by the onset of disease. And I just want to highlight a few symptoms that we also see in our mouse models, which are like ataxia. That means the coordination is kind of off, seizure, paralysis. So we are using a virus that has no associated disease. It's called adeno-associated virus. And we basically just put the healthy gene inside and then inject it intravenously. And we are using a dose that can efficiently target the entire brain. We are using 2 mouse models. One to answer the question, can we treat very early CANAVAN mice, so within the first 4 weeks of life. Okay, no. Okay, now we are back. And this mouse model has a very severe phenotype, and the life expectancy is around 4 weeks. And then we have a second mouse model that survives basically like a regular mouse, up to years. So the first question was, can we develop a gene therapy for CANAVAN disease that is effective and sustainable, meaning sustainable in this sense, you inject once and it treats the mouse for a lifetime, basically. So we used this first mouse model that usually dies after 4 weeks. And then measured weight. And what you can see here is untreated that the mice die very early. The black curve is a wild-type mouse. And then this is our first generation gene therapy. You see a difference between wild-type and the treated mice. And this is our second generation, which is improved and much stronger. You can see it equals the wild-type curve. And so next step, we tested them on motor function. Okay, now someone is interfering. Thank you. So the first mouse you're going to see is an untreated mouse. It's very sick, and it can barely stand on the rotor rod. And the speed of the rotor rod increases over time. And then you see here our 3rd generation gene therapy, 2nd generation, and a wild-type mouse. And they try their best to stay on top. So the 2nd generation mouse dropped off. Now the wild-type mouse fell off. In our 3rd generation gene therapies, which is the most potent we have so far, the mouse just keeps running. And it by far exceeds the performance of the wild-type mouse. So this particular mouse, it took 214 seconds versus 89. And if you, oops, no, next. And then if you look at the data after 1 year, you see here wild-type mice. First generation, those mice cannot perform at all. Second generation and third generation. Even after 1 year, those mice still have a better motor function on rotor rod than wild-type mice. Because it's so much fun to watch after 1 year. This time we put on 2 wild-type mice. Here's a female, here's a male. And this is the third generation treated mouse. As usual, the males give in early. The female wild type is also gone, and the treated CANAVAN mouse still runs. And then, so this is just motor function. What about brain pathology? So we looked at the brain slides, at the brain of those mice. You see here wild type. This is in MRI, first generation, second generation, third generation. And you can see in the first generation, after 1 year, you get these white signals back, which is basically the disease comes back. But in our third generation, it's completely gone. Still, the signal or the image looks like a wild type mouse. And then at one point, of course, we had to sacrifice the mice, and you look at the brain under the microscope, and you can see here different brain regions. It's probably hard to see from the back. But what you're looking for in CANAVAN is you see a lot of holes in the brain. So this is a wild-type mouse. You don't see any holes that are unexpected. This is our first generation. You can see here large parts of the brain are completely gone. Our second generation, you still have a few holes. I'm sorry. Oh, too fast. And this is our third generation. After 1 year, it looks completely normal, like wild type. Okay, so that kind of suggests we can design a gene therapy that is efficient and long-lasting. The second question was, how late can we treat? Because not always patients are diagnosed very early on in the disease process. So we used this second mouse model. Yeah. Okay. So we used the second mouse model and started treating those mice at juvenile age. And you see, back please. And you see wild-type mice here in black. The red curve is untreated. And then we are starting here. You see the untreated mice still have a lower weight, and after treatment they slowly catch up and equal wild-type mice. So even at a juvenile age, at least in the mouse model, they still recovered. Okay, next. And then we also tested them on rotor rod, of course. So here you have a wild-type mouse, and these are 3 different mice, all NER7 mice, all treated. So all CANAVAN mice, all treated at juvenile age. This one drops early. So you can see they're pretty close together in comparison to the wild-type mouse. Next one, please. And then if you do this with a lot of mice and you look at the data, at the statistics, so here is wild-type mouse. This is untreated at 1 year. Those ones were treated right after birth, and those were treated at juvenile age. So they can completely catch up and basically do as well as wild-type mice. Next one, please. And then again, we are looking at MRI to see how the brain in the living animals looks like. Here you see wild-type, untreated CD mouse. You see those white signals. Treated at P1, meaning right after birth. Treated at juvenile age. And you see it's completely normalized, like in wild type. And so I mentioned early NAA accumulates in the brain of CANAVAN mice, or CANAVAN patient actually. So we wanted to see, can we reduce NAA actually? And so at 1 year, we had different groups. One is here wild type. This is untreated. You see very high levels of NAA. Treated right after birth, treated as juvenile age. You see it's completely normalized. And the same is true for urine, where NAA classically also accumulates. Next. And then we moved even further. Now we started treating mice at adult age. You see here on the left a wild-type mouse. In the middle, an untreated mouse, you can see very severe movement disorder. It looks very skinny, a little hunched. And on the right, you see a mouse that was treated at adult age. 5 minutes? Okay, thanks. And they're basically moving as wild type. Can you go on one more? Okay. So I showed you a lot of motor function. But what about cognitive function, meaning memory function, for example? So we wanted to know, can we restore memory function in those mice? And one way of testing this is you can use, it's called T-maze. You put the mouse down here, there's a little door. Then you open the door, the mouse runs left or right. And you repeat this over and over again. And mice usually start alternating if they have normal memory function because they remember, oh, I've been in the left side, now I want to see what's on the right side. And so when you test mice at 7 months, here those mice were treated at adult age. Those are wild-type mice and those are untreated. You see that even if you treat them very late, they end up performing as well as wild-type mice. Next. And finally, we wanted to know, so CANAVAN disease is a leukodystrophy. You have a lot of brain damage in the white part of the brain. So we looked at, under electron microscopy, at the myelin. This is an untreated mouse at 7 weeks. You see only a few of these dark rings. Those are axons, and myelin is wrapped around it. And it looks very unorganized. And on the top, you see a wild-type mouse. You see many of those dark rings, which means those are all healthy axons with myelin around. Next. And this is 1 week after treatment. It still looks pretty messy, but so we waited basically 4 weeks total. Next one. And you see the untreated mouse, it gets actually worse. You see only very few of these dark rings, and you start seeing holes in the brain. Here you have a wild-type mouse, a lot of those dark rings as expected. Next. And then within 4 weeks after treatment, the myelin in the treated mouse completely came back, which suggests there's actually a great efficacy. Next. Okay, I tried to basically give an update what we have done, what is one part of our gene therapy approach. One is, can we design an effective and sustained treatment? Can we treat late CANAVAN mice and still rescue them? And I hope I could convince you that, at least in the mouse model, I think we did a pretty good job. Next one. And this, of course, needs a lot of people, very dedicated people that work on this project. Several people are more or less involved. And, of course, Dr. Gao as the PI, who is the main driving force in this approach. And of course, we had a lot of funding, including NTSAD, and I'm happy to answer any questions later. Thanks.
Well, thank you very much for that really incredibly promising progress that's been made. Again, just showing how funding at the right time can really drive progress in research. So thank you very much. That's looking really remarkable. So we've seen a super mouse on the rotor rod.